The Linux system. This chapter presents an in-depth examination of the Linux operating system. By examining a complete, real system, we can see how the concepts we have discussed relate both to one another and to practice. Linux is a variant of Unix that has gained popularity over the last several decades, powering devices as small as mobile phones and as large as room-filling supercomputers. In this chapter, we look at the history and development of Linux and cover the user and programmer interfaces that Linux presents, interfaces that owe a great deal to the Unix tradition. We also discuss the design and implementation of these interfaces. Linux is a rapidly evolving operating system. This chapter describes developments through the Linux 3.2 kernel, which was released in 2012. The Linux file system. Linux history. Linux looks and feels much like any other Unix system. Indeed, Unix compatibility has been a major design goal of the Linux project. However, Linux is much younger than most Unix systems. Its development began in 1991 when a Finnish university student, Linus Torvalds, began developing a small but self-contained kernel for the 80386 processor, the first true 32-bit processor in Intel's range of PC-compatible CPUs. Early in its development, the Linux source code was made available free both at no cost and with minimal distributional restrictions on the Internet. As a result, Linux's history has been one of collaboration by many developers from all around the world, corresponding almost exclusively over the Internet. From an initial kernel that partially implemented a small subset of the Unix system services, the Linux system has grown to include all of the functionality expected of a modern Unix system. In its early days, Linux development revolved largely around the central operating system kernel, the core, privileged executive that manages all system resources and interacts directly with the computer hardware. We need much more than this kernel, of course, to produce a full operating system. We thus need to make a distinction between the Linux kernel and a compatible Linux system. The Linux kernel is an original piece of software developed from scratch by the Linux community. The Linux system, as we know it today, includes a multitude of components, some written from scratch, others borrowed from other development projects, and still others created in collaboration with other teams. The basic Linux system is a standard environment for applications and user programming, but it does not enforce any standard means of managing the available functionality as a whole. As Linux has matured, a need has arisen for another layer of functionality on top of the Linux system. This need has been met by various Linux distributions. A Linux distribution includes all the standard components of the Linux system, plus a set of administrative tools to simplify the initial installation and subsequent upgrading of Linux, and to manage installation and removal of other packages on the system. A modern distribution also typically includes tools for management of file systems, creation and management of user accounts, administration of networks, web browsers, word processors, and so on. Design principles. In its overall design, Linux resembles other traditional non-microkernel Unix implementations. It is a multi-user, preemptively multitasking system with a full set of Unix-compatible tools. Linux's file system adheres to traditional Unix semantics, and the standard Unix networking model is fully implemented. The internal details of Linux's design have been influenced heavily by the history of this operating system's development. Although Linux runs on a wide variety of platforms, it was originally developed exclusively on PC architecture. A great deal of that early development was carried out by individual enthusiasts rather than by well-funded development or research facilities, So from the start, Linux attempted to squeeze as much functionality as possible from limited resources. Today, Linux can run happily on a multiprocessor machine with many gigabytes of main memory and many terabytes of disk space, but it is still capable of operating usefully in under 16 MB of RAM. As PCs became more powerful and as memory and hard disks became cheaper, the original minimalist Linux kernels grew to implement more Unix functionality. Speed and efficiency are still important design goals, but much recent and current work on Linux has concentrated on a third major design goal, standardization. One of the prices paid for the diversity of Unix implementations currently available is that source code written for one may not necessarily compile or run correctly on another. Even when the same system calls are present on two different Unix systems, they do not necessarily behave in exactly the same way. The POSIX standards comprise a set of specifications for different aspects of operating system behavior. There are POSIX documents for common operating system functionality and for extensions such as process threads and real-time operations. Linux is designed to comply with the relevant POSIX documents, and at least two Linux distributions have achieved official POSIX certification because it gives standard interfaces to both the programmer and the user. Linux presents few surprises to anybody familiar with the Unix. We do not detail these interfaces here. The sections on the programmer interface and user interface of BSD apply equally well to Linux. By default, however, the Linux programming interface adheres to SVR4 Unix semantics rather than to BSD behavior. A separate set of libraries is available to implement BSD semantics in places where the two behaviors differ significantly. Many other standards exist in the Unix world, but full certification of Linux with respect to these standards is sometimes slowed because certification is often available only for a fee, and the expense involved in certifying an operating system's compliance with most standards is substantial. However, supporting a wide base of applications is important for any operating system, so implementation of standards is a major goal for Linux development, even if the implementation is not formally certified. In addition to the basic POSIX standard, Linux currently supports the POSIX threading extensions, pthreads, and a subset of the POSIX extensions for real-time process control. Components of a Linux system. The Linux system is composed of three main bodies of code in line with most traditional Unix implementations. Kernel. The kernel is responsible for maintaining all the important abstractions of the operating system, including such things as virtual memory and processes. System libraries. The system libraries define a standard set of functions through which applications can interact with the kernel. These functions implement much of the operating system functionality that does not need the full privileges of kernel code. The most important system library is the C library known as libc. In addition to providing the standard C library, libc implements the user mode side of the Linux system call interface as well as other critical system-level interfaces. System utilities. The system utilities are programs that perform individual, specialized management tasks. Some system utilities are invoked just once to initialize and configure some aspects of the system. Others, known as daemons in Unix terminology, runs permanently, handling such tasks as responding to incoming network connections, accepting logon requests from terminals, and updating log files. Figure below illustrates the various components that make up a full Linux system. The most important distinction here is between the kernel and everything else. All the kernel code executes in the process's privileged mode with full access to all the physical resources of the computer. Linux refers to this privileged mode as kernel mode. Under Linux, no user code is built into the kernel. Any operating system support code that does not need to run in kernel mode is placed into the system libraries and runs in user mode. Unlike kernel mode, user mode has access only to a controlled subset of the system's resources. Kernel modules. The Linux kernel has the ability to load and unload arbitrary sections of kernel code on demand. These loadable kernel modules run in privileged kernel mode and as a consequence have full access to all the hardware capabilities of the machine on which they run. In theory, there is no restriction on what a kernel module is allowed to do. Among other things, a kernel module can implement a device driver, a file system, or a networking protocol. Kernel modules are convenient for several reasons. Linux's source code is free, so anybody wanting to write kernel code is able to compile a modified kernel and to reboot into that new functionality. However, recompiling, relinking, and reloading the entire kernel is a cumbersome cycle to undertake when you are developing a new driver. If you use kernel modules, you do not have to make a new kernel to test a new driver. The driver can be compiled on its own and loaded into the already running kernel. Of course, once a new driver is written, it can be distributed as a module so that other users can benefit from it without having to rebuild their kernels. This latter point has another implication because it is covered by the GPL license. The Linux kernel cannot be released with proprietary components added to it unless those new components are also released under the GPL and the source code for them is made available on demand. The kernel's module interface allows third parties to write and distribute on their own terms device drivers or file systems that could not be distributed under the GPL. Kernel modules allow a Linux system to be set up with a standard minimal kernel without any extra device drivers built in. Any device drivers that the user needs can be either loaded explicitly by the system at startup or loaded automatically by the system on demand and unloaded when not in use. For example, a mouse driver can be loaded when a USB mouse is plugged into the system and unloaded when the mouse is unplugged. The module support under Linux has 4 components. The module management system allows modules to be loaded into memory and to communicate with the rest of the kernel. The module loader and unloader, which are user mode utilities, work with the module management system to load a module into memory. The driver registration system allows modules to tell the rest of the kernel that a new driver has become available. A conflict resolution mechanism allows different device drivers to reserve hardware resources and to protect those resources from accidental use by another driver. Process management. A process is the basic context in which all user-requested activity is serviced within the operating system. To be compatible with other Unix systems, Linux must use a process model similar to those of other versions of Unix. Linux operates differently from the Unix in a few key places. However, in this section we review the traditional Unix process model and introduce Linux's threading model. The fork function and execute function process model. The basic principle of Unix process management is to separate into 2 steps 2 operations that are usually combined into one, the creation of a new process and the running of a new program. A new process is created by the fork function system call and a new program is run after a call to the execute function. These are 2 distinctly separate functions. We can create a new process with fork function without running a new program. The new subprocess simply continues to execute exactly the same program at exactly the same point that the first parent process was running. In the same way, Running a new program does not require that a new process be created first. Any process may call execute function at any time. A new binary object is loaded into the process's address space, and the new executable starts executing in the context of the existing process. This model has the advantage of great simplicity. It is not necessary to specify every detail of the environment of a new program in the system call that runs that program. The new program simply runs in its existing environment. If the parent process wishes to modify the environment in which a new program is to be run, it can fork and then, still running the original executable in a child process, make any system calls it requires to modify that child process before finally executing the new program. Under Unix, then, a process encompasses all the information that the operating system must maintain to track the context of a single execution of a single program. Under Linux, we can break down this context into a number of specific sections. Broadly, process properties fall into three groups: the process identity, environment, and context. Process identity. A process identity consists mainly of the following items: process ID, PID. Each process has a unique identifier. The PID is used to specify the process to the operating system when an application makes and associate the process with a process group, typically a tree of processes forked by a single user command and login session. Credentials. Each process must have an associated user ID and one or more group IDs that determine the rights of a process to access system resources and files. Personality. Process personalities are not traditionally found on Unix systems, but under Linux, each process has an associated personality identifier that can slightly modify the semantics of certain system calls. Personalities are primarily used by emulation libraries to request that system calls be compatible with certain varieties of Unix. Namespace. Each process is associated with a specific view of the file system hierarchy called its namespace. Most processes share a common namespace and thus operate on a shared file system hierarchy. Processes and their children can, however, have different namespaces, each with a unique file system hierarchy, their own root directory, and a set of mounted file systems. Most of these identifiers are under the limited control of the process itself. This process group and session identifiers can be changed if the process wants to start a new group or session. Its credentials can be changed subject to appropriate security checks. However, the primary PID of a process is unchangeable and uniquely identifies that process until termination. Process environment. A process's environment is inherited from its parent and is composed of two null-terminated vectors, the argument vector and the environment vector. The argument vector simply lists the command line arguments used to invoke the running program. It conventionally starts with the name of the program itself. The environment vector is a list of name equals value pairs that associates named environment variables with arbitrary textual values. The environment is not held in kernel memory but is stored in the process's own user mode address space as the first datum at the top of the process's stack. The argument environment vectors are not altered when a new process is created. The new child process will inherit the environment of its parent. However, a completely new environment is set up when a new program is invoked. On calling execute function, a process must supply the environment for the new program. The kernel passes these environment variables to the next program, replacing the process's current environment. The kernel otherwise leaves the environment and command line vectors alone, They are interpretations left entirely to the user mode libraries and applications. The passing of environment variables from one process to the next and the inheriting of these variables by the children of a process provide flexible ways to pass information to components of the user mode system software. Various important environment variables have conventional meanings to related parts of the system software. For example, the term variable is set up to name the type of terminal connected to a user's login session. Many programs use this variable to determine how to perform operations on the user's display, such as moving the cursor and scrolling a region of text. Programs with multilingual support use the lang variable to determine the language in which to display system messages for programs that include multilingual support. The environment variable mechanism custom tailors the operating system on a per-process basis. Users can choose their own languages or select their own editors independently of one another. Process context. The process identity and environment properties are usually set up when a process is created and not changed until that process exits. A process may choose to change some aspects of its identity if it needs to do so, or it may alter its environment. In contrast, process context is the state of the running program at any one time. It changes constantly. Process context includes the following parts. Scheduling context. The most important part of the process context is its scheduling context, the information that the scheduler suspend and restart the process. This information includes saved copies of all the process's registers. Floating point registers are stored separately and are restored only when needed. Thus, processes that do not use floating point arithmetic do not incur the overhead of saving that state. The scheduling context also includes information about scheduling priority and about any outstanding signals waiting to be delivered to the process. A key part of the scheduling context is the process's kernel stack, a separate area of kernel memory reserved for use by kernel mode code. Both system calls and interrupts that occur while the process is executing will use the stack. Accounting. The kernel maintains accounting information about the resources currently being consumed by each process and the total resources consumed by the process in its entire lifetime so far. File table. The file table is an array of pointers to kernel file structures representing open files. When making file I/O system calls, processors refer to files by an integer known as a file descriptor (FD) that the kernel uses to index into this table. File system context. Whereas the file table lists the existing open files, the file system context applies to requests to open new files. The file system context includes the process's root directory, current working directory, and namespace. Signal handler table. Unix systems can deliver asynchronous signals to a process in response to various external events. The signal handler table defines the action to take in response to a specific signal. Valid actions include ignoring the signal, terminating the process, and invoking a routine in the process's address space. Scheduling. Scheduling is the job of allocating CPU time to different tasks within an operating system. Linux, like all Unix systems, supports preemptive multitasking. In such a system, the process scheduler decides which process runs and when. Making these decisions in a way that balances fairness and performance across many different workloads is one of the more complicated challenges in modern operating systems. Normally, we think of scheduling as the running and interrupting of user processes, but another aspect of scheduling is also important to Linux, the running of the various kernel tasks. Kernel tasks encompass both tasks that are requested by a running process and tasks that execute internally on behalf of the kernel itself, such as tasks spawned by Linux's I/O subsystem. Process scheduling. Linux has process scheduling algorithms. One is a time-sharing algorithm for fair, preemptive scheduling among multiple processes. The other is designed for real-time tasks where absolute priorities are more important than fairness. Earlier versions ran a variation of the traditional Unix scheduling algorithm. This algorithm does not provide adequate support for SMP systems, does not scale well as the number of tasks on the system grows, and does not maintain fairness among interactive tasks, particularly on systems such as desktops and mobile devices. Version 2.5 implemented a scheduling algorithm that selects which task to run in constant time, known as O1, regardless of the number of tasks or processes in the system. The new scheduler also provided increased support for SMP, including processor affinity and load balancing. These changes, while improving scalability, did not improve interactive performance or fairness, and, in fact, made these problems worse under certain workloads. Consequently, the process scheduler was overhauled a second time with Linux kernel version 2.6. This version ushered in the completely fair scheduler CFS. The Linux scheduler is a preemptive, priority-based algorithm with two separate priority ranges, a real-time range from 0 to 99 and a nice value ranging from 20 to 19. Smaller nice values indicate higher priorities. Thus, by increasing the nice value, you are decreasing your priority and being nice to the rest of the system. CFS is a significant departure from the traditional Unix process scheduler. In the latter, the core variables in the scheduling algorithm are priority and time slice. The time slice is the length of time, the slice of the processor that a process is afforded. Traditional Unix systems give processes a fixed time slice, perhaps with a boost or penalty for high or low priority processes respectively. A process may run for the length of its time slice, and higher priority processes run before lower priority processes. It is a simple algorithm that many non-Unix systems employ. Such simplicity worked well for the early time-sharing systems, but has proved incapable of delivering good interactive performance and fairness on today's modern desktops and mobile devices. CFS introduced a new scheduling algorithm called fair scheduling that eliminates time slices in the traditional sense. Instead of time slices, all processes are allotted a proportion of the process's time. CFS calculates how long a process should run as a function of the total number of runnable processes. Memory management. Memory management under the Linux has two components. The first deals with allocating and freeing physical memory, pages, groups of pages, and small blocks of RAM. The second handles virtual memory, which is memory mapped into the address space of running processes. In this section, we describe these two components and then examine the mechanisms by which the loadable components of a new program are brought into a process's virtual memory in response to an execute function system call. Management of physical memory. Due to specific hardware constraints, Linux separates physical memory into 4 different zones or regions. Zone DMA, Zone DMA32, Zone Normal, Zone High Mem. These zones are architecture specific. For example, on the Intel x86-32 architecture, certain ISA, industry standard architecture devices can only access the lower 16 MB of physical memory using DMA. On these systems, the first 16 MB of physical memory comprise Zone DMA. On other systems, certain devices can only access the first 4 GB of physical memory despite supporting 64-bit addresses. On such systems, the first 4 GB of physical memory comprise Zone DMA32. Zone High Mem for high memory refers to physical memory that is not mapped into the kernel address space. For example, on the 32-bit Intel architecture where 232 provides a 4 GB address space, the kernel is mapped into the first 896 MB of the addressing space. The remaining memory is referred to as high memory and is allocated from Zone High Mem. Finally, Zone Normal comprises everything else, the normal, regularly mapped pages. Whether an architecture has a given zone depends on its constraints. A modern 64-bit architecture such as Intel x86-64 has a small 16 MB zone DMA for legacy devices and all the rest of its memory in Zone Normal with no high memory. The relationship of zones and physical addresses on the Intel x86-32 architecture is shown in figure below. The kernel maintains a list of free pages for each zone. When a request for physical memory arrives, the kernel satisfies the request using the appropriate zone. The primary physical memory manager in the Linux kernel is the page allocator. Each zone has its own allocator, which is responsible for allocating and freeing all physical pages for the zone and is capable of allocating ranges of physically contiguous pages on request. The allocator uses a buddy system to keep track of available physical pages. In this scheme, adjacent units of allocatable memory are paired together, hence its name. Each allocatable memory region has an adjacent partner or buddy. Whenever two allocated partner regions are freed up, they are combined to form a larger region, a buddy heap. That larger region also has a partner with which it can combine to form a still larger free region. Conversely, if a small memory request cannot be satisfied by allocation of an existing small free region, then a larger free region will be subdivided into two partners to satisfy the request. Separate linked lists are used to record the free memory regions of each allowable size. Under Linux, the smallest size allocatable under this mechanism is a single physical page. Figure below shows an example of buddy heap allocation. A 4 KB region is being allocated, but the smallest available region is 16 KB. The region is broken up recursively until a piece of the desired size is available. Ultimately, all memory allocations in the Linux kernel are made either statically by drivers that reserve a contiguous area of memory during system boot time or dynamically by the page allocator. However, kernel functions do not have to use the basic allocator to reserve memory. Several specialized memory management subsystems use the underlying page allocator to manage their own pools of memory. The most important are the virtual memory system, the kmalloc function variable length allocator, the slab allocator used for allocating memory for kernel data structures, and the page cache used for caching pages belonging to files. Many components of the Linux operating system need to allocate entire pages on request, but often smaller blocks of memory are required. The kernel provides an additional allocator for arbitrary sized requests, where the size of a request is not known in advance and may be only a few bytes. Analogous to the C language's malloc function, this kmalloc function serve allocates entire physical pages on demand but then splits them into smaller pieces. The kernel maintains lists of pages in use by the kmalloc function service. Allocating memory involves determining the appropriate list and either taking the first free piece available on the list or allocating a new page and splitting it up. Memory regions claimed by the kmalloc function system are allocated permanently until they are freed explicitly with the corresponding call to kfree function. The kmalloc function system cannot reallocate or reclaim these regions in response to memory shortages. Another strategy adopted by Linux for allocating kernel memory is known as slab allocation. A slab is used for allocating memory for kernel data structures and is made up of one or more physically contiguous pages. A cache consists of one or more threads, slabs. There is a single cache for each unique kernel data structure. For example, a cache for the data structure representing process descriptors, a cache for file objects, a cache for inodes, and so forth. Each cache is populated with objects that are instantiations of the kernel data structure the cache represents. For example, the cache representing inodes stores instances of inode structures, and the cache representing process descriptors stores instances of process descriptor structures. The relationship among slabs, caches, and objects is shown in figure below. The figure shows two kernels objects 3 KB in size and 3 objects 7 KB in size. These objects are stored in the respective caches for 3 KB and 7 KB objects. The slab allocation algorithm uses caches to store kernel objects. When a cache is created, a number of objects are allocated to the cache. The number of objects in the cache depends on the size of the associated slab. For example, a 12 KB slab made up of 3 contiguous 4 KB pages could store 6 2 KB objects. Initially, all the objects in the cache are marked as free. When a new object for a kernel data structure is needed, the allocator can assign any free object from the cache to satisfy the request. The object assigned from the cache is marked as used. Let's consider a scenario in which the kernel requests memory from the slab allocator for an object representing a process descriptor. In Linux systems, a process descriptor is one of the type struct task struct which requires approximately 1.7 KB of memory. When the Linux kernel creates a new task, it requests the necessary memory for the struct task struct object from its cache. The cache will fulfill the request using a struct task struct object that has already been allocated in a slab and is marked as free. In Linux, a slab may be in one of the 3 possible states. Full. All objects in the slab are marked as used. Empty. All objects in the slab are marked as free. Partial. The slab consists of both used and free objects. Virtual memory. The Linux virtual memory system is responsible for maintaining the address space accessible to each process. It creates pages of virtual memory on demand and manages loading those pages from disk and swapping them back out to disk as required. Under Linux, the Virtual Memory Manager maintains 2 separate views of a process's address space, as a set of separate regions and as a set of pages. The first view of an address space is the logical view, describing instructions that the virtual memory system has received concerning the layout of the address space. In this view, the address space consists of a set of non-overlapping regions, each region representing a contiguous, page-aligned subset of the address space. Each region is described internally by a single VM-area struct structure that defines the properties of the region, including the process's read, write, and execute permissions in the region, as well as information about any files associated with the region. The regions for each address space are linked into a balanced binary tree to allow fast lookup of the region corresponding to any virtual address. File systems. Linux retains Unix's standard file system model. In Unix, a file does not have to be an object stored on disk or fetched over a network from a remote file server. Rather, Unix files can be anything capable of handling the input or output of a stream of data. Device drivers can appear as files, and inter-process communication channels or network connections also look like files to the user. The Linux kernel handles all these types of files by hiding the implementation details of any single file type behind a layer of software, the Virtual File System, VFS. Here we first cover the Virtual File System and then discuss the standard Linux file system, ext3. The Virtual File System. The Linux VFS is designed around object-oriented principles. It has two components, a set of definitions that specify what file system objects are allowed to look like and a layer of software to manipulate the objects. The VFS defines four main object types. An inode object represents an individual file. A file object represents an open file. A superblock object represents an entire file system. A directory object represents an individual directory entry. For each of these four object types, the VFS defines a set of operations. Every object of one of these types contains a pointer to a function table. The function table lists the addresses of the actual functions that implement the defined operations for that object. For example, an abbreviated API for some of the file objects operations includes integer open, provided in brackets, open a file, size tread, provide in brackets, read from a file, size twrite, provide in brackets, write to a file, integer mmap, write in brackets, memory map a file. The complete definition of the file object is specified in the struct file operations, which is located in the file /usr/include/linux/fs.h. An implementation of the file object for a specific file type is required to implement each function specified in the definition of the file object. The VFS software layer can perform an operation on one of the file system objects by calling the appropriate function from the object's function table without having to know in advance exactly what kind of object it is dealing with. The VFS does not know or care whether an inode represents a networked file, a disk file, a network socket, or a directory file. The appropriate function for that file's read function operation will always be at the same place in its function table, and the VFS software layer will call that function without caring how the data are actually read. Inode. The inode and file objects are mechanisms used to access files. An inode object is a data structure containing pointers to the disk blocks that contain the actual file contents, and a file object represents a point of access to the data in an open file. A process cannot access an inode's contents without first obtaining a file object pointing to the inode. The file object keeps track of where in the file the process is currently reading or writing to keep track of sequential file I/O. It also remembers the permissions, for example read or write, requested when the file was opened, and tracks the process's activity if necessary to perform adaptive read-ahead, fetching file data into memory before the process requests the data to improve performance. File objects typically belong to a single process, but inode objects do not. There is one file object for every instance of an open file, but always only a single inode object. Even when a file is no longer in use by any process, its inode object may still be cached by the VFS to improve performance if the file is used again in the near future. All cached file data are linked onto a list in the file's inode object. The inode also maintains standard information about each file, such as the owner, size, and time most recently modified. Directory files are dealt with slightly differently from other files. The Unix programming interface defines a number of operations on directories, such as creating, deleting, and renaming a file in a directory. The system calls for these directory operations do not require that the user open the files concerned, unlike the case for reading or writing data. The VFS therefore defines these directory operations in the inode object rather than in the file object. The superblock object represents a connected set of files that form a self-contained file system. The operating system kernel maintains a single superblock object for each disk device mounted as a file system and for each networked file system currently connected. The main responsibility of the superblock object is to provide access to inodes. The VFS identifies every inode by a unique file system /inode number pair, and it finds the inode corresponding to a particular inode number by asking the superblock object to return the inode with that number. Finally, a dentry object represents a directory entry which may include the name of a directory in the path name of a file such as /usr or the actual file such as studio.h. For example, the file /usr/include/studio.h contains the directory entries 1/2 usr, 3 include, and 4 studio.h. Each of these values is represented by a separate dentry object. The Linux process file system. The flexibility of the Linux VFS enables us to implement a file system that does not store data persistently at all, but rather provides an interface to some other functionality. The Linux process file system, known as the /proc file system, is an example of a file system whose contents are not actually stored anywhere, but are computed on demand according to user file I/O requests. A /proc file system is not unique to Linux. SVR for Unix introduced a /proc file system as an efficient interface to the kernel's process debugging support. Each subdirectory of the file system corresponded not to a directory on any disk, but rather to an active process on the current system. A listing of the file system reveals one directory per process, with the directory name being the ASCII decimal representation of the processor's unique process identifier, PID. Linux implements such a /proc file system, but extends it greatly by adding a number of extra directories and text files under the file system's root directory. These new entries correspond to various statistics but the kernel and the associated loaded drivers. The /proc file system provides a way for programs to access this information as plain text files. The standard Unix user environment provides powerful tools to process such files. For example, in the past, the traditional Unix ps command for listing the states of all running processes has been implemented as a privileged process that reads the process state directly from the kernel's virtual memory. Under Linux, the command is implemented as an entirely unprivileged program that simply passes and formats the information from /proc. The /proc file system must implement two things: a directory structure and the file contents within. Because a Unix file system is defined as a set of file and directory inodes identified by their inode numbers, the /proc file system must define a unique and persistent inode number for each directory and the associated files. Input and output. To the user, the I/O system in Linux looks much like that in any Unix system. That is, to the extent possible, all device drivers appear as normal files. Users can open an access channel to a device in the same way they open any other file devices can appear as objects within the file system. The system administrator can create special files within a file system that contain references to a specific device driver, and a user opening such a file will be able to read from and write to the device referenced. By using the normal file protection system, which determines who can access which file, the administrator can set access permissions for each device. Linux splits all devices into three classes: block devices, character devices, and network devices. Figure below illustrates the overall structure of the device driver system. Block devices include all devices that allow random access to completely independent, fixed-size blocks of data, including hard disks and floppy disks, CD-ROMs and Blu-ray disks, and flash memory. Block devices are typically used to store file systems, but direct access to a block device is also allowed so that programs can create and repair the file system that the device contains. Applications can also access these block devices directly if they wish. For example, a database application may prefer to perform its own fine-tuned layout of data onto a disk rather than using the general-purpose file system. Character devices include most other devices such as mice and keyboards. The fundamental difference between block and other character devices is random access. Block devices are accessed randomly, while character devices are accessed serially. For example, seeking a certain position in a file might be supported for a DVD but makes no sense for a pointing device such as a mouse. Network devices are dealt with differently from block and character devices. Users cannot directly transfer data to network devices. Block devices. Block devices provide the main interface to all disk devices in a system. Performance is particularly important for disks, and the block device system must provide functionality to ensure that disk access is as fast as possible. The functionality is achieved through the scheduling of I/O operations. In the context of block devices, a block represents the unit with which the kernel performs I/O. When a block is read into memory, it is stored in a buffer. The request manager is the layer of software that manages the reading and writing of buffer contents to and from a block device driver. A separate list of requests is kept for each block device driver. Traditionally, these requests have been scheduled according to a unidirectional elevator C-scan algorithm that exploits the order in which requests are inserted in and removed from the lists. The request lists are maintained in sorted order of increasing starting sector number. When a request is accepted for processing by a block device driver, it is not removed from the list. It is removed only after the I/O is complete, at which point the driver continues with the next request in the list, even if new requests have been inserted in the list before the active request. As new I/O requests are made, the request manager attempts to merge requests in the lists. Linux kernel version 2.6 introduced a new I/O scheduling algorithm. Although a simple elevator algorithm remains available, the default I/O scheduler is now the completely fair queuing CFQ scheduler. The CFQ I/O scheduler is fundamentally different from elevator-based algorithms. Instead of sorting requests into a list, CFQ maintains a set of lists, by default, one for each process. Requests originating from a process go in that process's list. For example, if two processes are issuing I/O requests, CFQ will maintain two separate lists of requests, one for each process. The lists are maintained according to the C-scan algorithm. CFQ services the lists differently as well. When a traditional C-scan algorithm is indifferent to a specific process, CFQ services each process's list round-robin. It pulls a configurable number of requests, by default 4, from each list before moving on to the next. This method results in fairness at the process level. Each process receives an equal fraction of the disk's bandwidth. The result is beneficial with interactive workloads where I/O latency is important. In practice, however, CFQ performs well with most workloads. Inter-process communication. Linux provides a rich environment for processes to communicate with each other. Communication may be just a matter of letting another process know that some event has occurred, or it may involve transferring data from one process to another. Synchronization and signals. The standard Linux mechanism for informing a process that an event has occurred is the signal. Signals can be sent from any process to any other process, with restrictions on signals sent to processes owned by another user. However, a limited number of signals are available and they cannot carry information. Only the fact that a signal has occurred is available to a process. Signals are not generated only by processes. The kernel also generates signals internally. For example, it can send a signal to a server process when data arrive on a network channel, to a parent process when a child terminates, or to a waiting process when a timer expires. Internally, the Linux kernel does not use signals to communicate with processes running in kernel mode. If a kernel mode process is expecting an event to occur, it will not use signals to receive notification of that event. Rather, communication about incoming asynchronous events within the kernel takes place through the use of scheduling states and wait queue structures. These mechanisms allow kernel mode processes to inform one another about relevant events, and they also allow events to be generated by device drivers or by the networking system. Whenever a process wants to wait for some event to complete, it places itself on a wait queue associated with that event and tells the scheduler that it is no longer eligible for execution. Once the event has completed, every process on the wait queue will be awoken. This procedure allows multiple processes to wait for a single event. For example, if several processes are trying to read a file from a disk, then they will all be awakened once the data have been read into memory successfully. Although signals have always been the main mechanism for communicating asynchronous events among processes, Linux also implements the semaphore mechanism of System V Unix. A process can wait on a semaphore as easily as it can wait for a signal, but semaphores have two advantages. Large numbers of semaphores can be shared among multiple independent processes, and operations on multiple semaphores can be performed atomically. Internally, the standard Linux wait queue mechanism synchronizes processes that are communicating with semaphores. Passing of data among processes. Linux offers several mechanisms for passing data among processes. The standard Unix pipe mechanism allows a child process to inherit a communication channel from its parent. Data written to one end of the pipe can be read at the other. Under Linux, pipes appear as just another type of inode to virtual file system software, and each pipe has a pair of wait queues to synchronize the reader and writer. Unix also defines a set of networking facilities that can send streams of data to both local and remote processes. Another process communications method, shared memory, offers an extremely fast way to communicate large or small amounts of data. Any data written by one process to a shared memory region can be read immediately by any other process that has mapped that region into its address space. The main disadvantage of shared memory is that, on its own, it offers no synchronization. A process can neither ask the operating system whether a piece of shared memory has been written to, nor suspend execution until such a write occurs. Shared memory becomes particularly powerful when used in conjunction with another interprocess communication mechanism that provides the missing synchronization. A shared memory region in Linux is a persistent object that can be created or deleted by processes. Such an object is treated as though it were a small independent address space. The Linux paging algorithms can elect to page shared memory pages out to disk just as they can page out a process's data pages. The shared memory object acts as a backing store for shared memory regions, just as a file can act as a backing store for a memory-mapped memory region. When a file is mapped into a virtual address space region, then any page faults that occur cause the appropriate page of the file to be mapped into virtual memory. Similarly, shared memory mappings direct page faults to map in pages from a persistent shared memory object. Also, just as for files, shared memory objects remember their contents even if no processes are currently mapping them into virtual memory. Network structure. Networking is a key area of functionality for Linux. Not only does Linux support the standard Internet protocols used for most Unix to Unix communications, but it also implements a number of protocols native to other non-Unix operating systems. In particular, since Linux was originally implemented primarily on PCs rather than on large workstations or on server-class systems, it supports many of the protocols typically used on PC networks such as AppleTalk and IPX. Internally, networking in the Linux kernel is implemented by 3 layers of software. 1. The socket interface. 2. Protocol drivers. 3. Network device drivers. User applications perform all networking requests through the socket interface. This interface is designed to look like the 4.3 BSD socket layer so that any programs designed to make use of Berkeley sockets will run on Linux without any source code changes. The BSD socket interface is sufficiently general to represent network addresses for a wide range of networking protocols. This single interface is used in Linux to access not just those protocols implemented on standard BSD systems, but all the protocols supported by the system. The next layer of software is the protocol stack, which is similar in organization to SD's own framework. Whenever any networking data arrive at this layer, either from an application's socket or from a network device driver, the data are expected to have been tagged with an identifier specifying which network protocol they contain. Protocols can communicate with one another if they desire. For example, within the Internet protocol set, separate protocols manage routing, error reporting, and reliable retransmission of lost data. The protocol layer may rewrite packets, create new packets, split or reassemble packets into fragments, or simply discard incoming data. Ultimately, once the protocol layer has finished processing a set of packets, it passes them on either upward to the socket interface if the data are destined for a local connection, or downward to a device driver if the data need to be transmitted remotely. The protocol layer decides to which socket or device it will send the packet. All communication between the layers of the networking stack is performed by passing single skbuf socket buffer structures. Each of these structures contains a set of pointers into a single continuous area of memory, representing a buffer inside which network packets can be constructed. The valid data in a skbuf do not need to start at the beginning of the skbuf's buffer, and they do not need to run to the end. The networking code can add data to or trim data from either end of the packet as long as the result still fits into the skbuf. This capacity is especially important on modern microprocessors where improvements in CPU speed have far outstripped the performances of main memory. The skbuf architecture allows flexibility in manipulating packet headers and checksums while avoiding any unnecessary data copying. Security. Linux's security model is closely related to typical Unix security mechanisms. The security concerns can be classified into two groups. Authentication, making sure that nobody can access the system without first providing that she has entry rights. Access control, providing a mechanism for checking whether a user has the right to access a certain object and preventing access to objects as required. Authentication. Authentication in Unix has typically been performed through the use of a publicly readable password file. A user's password is combined with a random salt value and the result is encoded with a one-way transformation function and stored in the password file. The use of the one-way function means that the original password cannot be deduced from the password file except by trial and error. When a user presents a password to the system, the password is recombined with the salt value stored in the password file and passed through the same one-way transformation. If the result matches the contents of the password file, then the password is accepted. A new security mechanism has been developed by Unix vendors to address authentication problems. The Pluggable Authentication Modules (PAM) system is based on a shared library that can be used by any system component that needs to authenticate users. An implementation of this system is available under Linux. PAM allows authentication modules to be loaded on demand as specified in a system-wide configuration file. If any new authentication mechanism is added at a later date, it can be added to the configuration file and all system components will immediately be able to take advantage of it. PAM modules can specify authentication methods, account restrictions, session setup functions, and password changing functions so that when users change their passwords, all the necessary authentication mechanisms can be updated at once. Access control. Access control under Unix systems, including Linux, is performed through the use of unique numeric identifiers. A user identifier (UID) identifies a single user or a single set of access rights. A group identifier (GID) is an extra identifier that can be used to identify rights belonging to more than one user. Access control is applied to various objects in the system. Every file available in the system is protected by the standard access control mechanism. In addition, other shared objects such as shared memory sections and semaphores employ the same access system. Every object in a Unix system under user and group access control has a single UID and a single GID associated with it. User processes also have a single UID, but they may have more than one GID. If a process's UID matches the UID of an object, then the process has user rights or owner rights to that object. If the UIDs do not match but any GID of the process matches the object's GID, then group rights are conferred. Otherwise, the process has world rights to the object. Linux performs access control by assigning objects a protection mask that specifies which access modes, read, write or execute, are to be granted to processes with owner, group or world access. Thus, the owner of an object might have full read, write and execute access to a file. Other users in a certain group might be given read access but denied write access, and everybody else might be given no access at all. Summary. Linux is a modern, free operating system based on Unix standards. It has been designed to run efficiently and reliably on common PC hardware. It also runs on a variety of other platforms such as mobile phones. It provides a programming interface and user interface compatible with standard Unix systems and can run a large number of Unix applications, including an increasing number of commercially supported applications. Linux has not evolved in a vacuum. A complete Linux system includes many components that were developed independently of Linux. The core Linux operating system kernel is entirely original, but it allows much existing free Unix software to run, resulting in an entire Unix-compatible operating system free from proprietary code. The Linux kernel is implemented as a traditional monolithic kernel for performance reasons, but it is modular enough in design to allow most drivers to be dynamically loaded and unloaded at runtime. Linux is a multi-user system providing protection between processes and running multiple processes according to a time-sharing scheduler. Newly created processes can share selective parts of the execution environment with their parent processes, allowing multi-threaded programming. Inter-process communication is supported by both system-V mechanisms, message queues, semaphores, and shared memory, and BSD's socket interface. Multiple networking protocols can be accessed simultaneously through the socket interface. The memory management system uses page sharing and copy on write to minimize the duplication of data shared by different processes. Pages are loaded on demand when they are first referenced and are paged back out to backing store according to an LFU algorithm if physical memory needs to be reclaimed. To the user, the file system appears as a hierarchical directory tree that obeys Unix semantics. Internally, Linux uses an abstraction layer to manage multiple file systems. Device-oriented networked and virtual file systems are supported. Device-oriented file systems access disk storage through a page cache that is unified with the virtual